Hello students, in today's class we are going to learn about methods for enumeration of growth. So these methods can be broadly divided into two categories, that is direct method where we are directly measuring the actual cells through microscopy, and the other types of methods are cultural methods where we are first growing the cells and then measuring them. These can again be by some methods such as pour plate and spread plate methods that we have learned in our laboratory, where we are actually counting each and every cell, while there are other methods that are indirect method where we are not actually measuring each and every cell, but we are correlating it with some of the parameters associated with the growth, such as turbidity. So as the growth will increase, the medium will become turbidity. So you can correlate the two. More the turbidity, more will be the growth. So we'll look at each of these methods. So the first method that we are going to discuss here is by making use of a hemocytometer state slide. So this is the image of a hemocytometer state slide, and it has these two regions which have marking on the slides. When you observe under the microscope, you'll be able to see that these marked region is divided into these square-like portions, and these four large squares on the corners are known as the WBC chambers, and the one in the center is known as the RBC chamber. So you can use any of the chambers for counting purposes. The main thing to pay attention over here is the dimensions of each of the chambers. So the length of each of these squares is 1 millimeter and the breadth is 1 millimeter, while the depth is about zero point 0.1 millimeter. So for getting the desired depth, what we have to do is we have to put a cover slip over here on top of the slide, and then we have to load our sample. So when we load over our sample, then automatically it will come to a depth of 0.1 millimeter. So with this information, we can calculate what is the volume of each of these squares. So volume of each of the square is going to be length into breadth into height. So that is equal to 1 millimeter multiplied by 1 millimeter multiplied by zero point 0.1 millimeter. So the total volume is going to be 0.1 millimeter cube. Also, there is a relation between the liquids and how much volume they occupy. So generally 1 ml of a liquid will occupy 1000 millimeter cube of volume. So this relationship is important, which we'll need for further calculation. So once we have the volume of our chamber, the next step is counting. So we need to basically go back to the previous slide. So we basically need to count the number of cells in each of these squares. Okay. So once we have the number in the squares, we can conclude that how many number of cells are present in one WBC chamber. For example, if there are 56 cells in one WBC chamber, that will mean that 56 cells are present in 0.1 millimeter cube of volume. Okay, so we need to find out how many cells are present in 1 ml. So we just need to multiply whatever number we get. It is present in 0.1 millimeter cube volume. To convert this 0.1 millimeter cube in 1000 millimeter cube volume, we need to multiply this by 10 to the power 4. Okay, that is 1 and 4 zeros. So we'll have to do that on either side. So that will mean by that 56 into 10 to the power 4 cells are present in 1000 millimeter cube volume, which is same as 1 ml of liquid. Okay, so using this you can find out how many cells are present per ml of the given liquid or sample. This is one problem. You can practice it to find out how many cells are present using these numbers. So here what they are doing is instead of one WBC chamber, they are counting all the four WBC chambers, and they have found out the average number of cells that are present per WBC chamber. So the average comes out to 66. So we have to simply multiply 66. So 66 will be present in zero point 0.1 millimeter cube. So we have to multiply it by 10 to the power 4. So that will be the number of cells that are present in 1 ml of the sample. Okay, so the next method that we are going to discuss here is measurement using a micrometer stage slide. So what is a micrometer stage slide? A micrometer stage slide has divisions on it, and the divisions are such that it is, you'll be able to, if you observe it by eye, you will be able to see some markings on the slide like these. And if you observe it under the microscope, you'll be able to see that there are actually 100 divisions that are present within this marked area. And this length of this marked area is actually 1 millimeter. And 1 millimeter is divided into 100 divisions. So there are these 10 large divisions, as you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 large divisions. And in between two large divisions, you will find 10 subdivisions. Okay, so this basically means that each small subdivision is equal to 0.01 millimeters in length. Now, what we have to do is you have to first observe the field of vision. So when you observe under the microscope, you basically see a circle like this, and this circle is known as your field of vision. So the first step over here is to find out what is the diameter of the field of vision, for which we'll be using this micrometer stage slide. You have to adjust the micrometer stage slide along the diameter of the field of vision. So in this example, you can see that the diameter is occupying about 1, 2, 3, 4, and 5 bigger lines, which means there are total 50 divisions, which means that the diameter of the field of vision is 50 divisions will correspond to 0.5 millimeter. So the diameter is 0.5 millimeter, and hence the radius becomes 0.25 millimeter. Using this information, you can calculate what is the area of the field of vision by the formula pi r squared. So it is going to be 3.14 multiplied by 0.25 square, which comes out to 0.196 millimeter square. So once we have the, what we have calculated right now is what is the area of one field of vision. Now the next step. Next step is to use the ordinary slide and mark an area of 1 centimeter square, basically of 1 centimeter by 1 centimeter on the slide using a glass marker pencil. Now the glass marker pencil, you know, it when you write on the slide, it kind of gives thick edges to it, and as a result, the sample will not flow out of the box that you are drawing. After that, you will load your sample that you want to analyze in the space. So about 100 microliters of liquid will fit easily in the space. Now we also know the area of a square is 1 centimeter multiplied by 1 centimeter, that is 1 centimeter square. Okay. So once you have this information, the next step is to count the number of cells present in per field of vision. So we will count at random 5 different fields of vision. Randomly, we will count here, here at 5 different locations. And these are the average numbers that I have, for example. These are the numbers that I have. After this, we need to take an average. Okay, so the question here is how many cells are present in 1 ml of the sample. So once we take the average, this is what we have. The average is 56.8 cells. Okay, so these average number of cells are present in one field of vision. Okay, we had already calculated the area of one field of vision as 0.196 millimeter square, which is same as when I am converting it to centimeter square, it is 0.00196 centimeters square. So 0.00196 centimeters square area is containing 56.8 cells. So what I need to do is convert this into 1 centimeter square. I have to find out how many cells will be present in 1 centimeter square area. So by simply cross multiplying, I can find out that if in 0.00196 centimeter square, 56.8 cells are present, then how many are present in 1 centimeter square? So I can do 1 multiplied by 56.8 divided by 0.00196. That gives me this number, 28976 cells. So these many cells are present in 1 centimeter square area, which corresponds to 100 microliters. Since we are loading 100 microliters, if I go to the previous slide, we are loading 100 microliter of sample in this area. Okay, so we have reached our conclusion that 28976 cells in 1000 microliters. So the question is how many are present per ml? So you have to just multiply it by 10. So that will give 2.8 into 10 to the power 5 cells per ml. The next method makes use of spectrophotometry. I think we are all aware spectrophotometry is basically uh, based on Beer-Lambert's law. So more the cell density, more will be the OD value that we will get when we read it in a spectrophotometer. So in this method, we first need to make a standard graph. Okay, so in standard graph, what we need to do is we will take different volumes of uh, like we'll take a liquid culture and we will take different volumes of the sample and measure its OD. Simultaneously, we'll also determine how many that OD or that sample will correspond to how many cell number by other methods such as spread plate method. Now, once we have these number, we will have a standard graph which will tell you that suppose point 1 is the OD, then whatever is the cell number that you can determine. Okay, and then now once you have the standard graph, what you need to do is you just need to take your sample and take its reading by comparing with the standard graph. If point 0.6 is the OD, by comparing in the graph, you can calculate the cell number that you have from the graph, and in this way you will be able to determine what is the cell number in your given sample. So here we have discussed about direct methods that make use of hemocytometer state slide, micrometer state slide. So like when you're doing the counting with these methods, you actually do not know the cells that you're counting are live cells or dead cell, unless we make use of a viable count method wherein we make use of a viable stain such as trypan blue. So here we are basically only staining the cells or whatever sample we are using with trypan blue, and the live cells will be colorless when you observe them, while the dead cells, since they do not have a system, the dye will enter into the cells, and as a result the dead cells will be appear will take up the dye and they will appear blue in color. So when you are observing under the microscope, if you are aiming at counting only the live cells, then you can count all the colorless cells and do all the calculations, so you will know what is the viable count. Then you also have cultural methods for viable count method, such as the pour plate and the spread plate method, which we have already learnt in the laboratory. So I'll not discuss it about it here. Then, so all these methods will be categorized into direct methods since we are directly measuring cell numbers. While there are other methods, that is spectrophotometry or turbidometry, where we are indirectly correlating turbidity with the cell number. Okay, so this method is known as indirect method. So that's it about various methods for measurement of growth. Kindly like, share, and subscribe if you like the content and to get the direct access to the uploaded video. Thank you.